So one last example problem, and I wanted to make sure that this was with a weak base, and I wanted to kind of show you a little bit more of a twisted problem. This is actually one of my favorite ones to do in this entire chapter. So we're going to take another ammonia solution, and all we know is that it has a pH of 11.37, and we're asked to calculate its molarity. There is stunningly little information inside of this problem, and yet as long as we're kind of writing down what we know and being methodical to the methodology that we've learned, we should be able to get through this problem with no sweat. So here's the first thing. We are told that we have ammonia. The very first thing we need, balanced chemical equation. So here we go. We have ammonia reacting with water. Again, water is necessary as this equation to try and produce the hydroxide on the other side. That NH3 is going to want to suck up one of the hydrogens off of the water to create the products. And because we know that this is an equilibrium, it's time to set up the chart problem underneath it. And let's again layer in the information that I know. I don't know the molarity of my NH3, so I'm actually going to label that as X. But I do know that initially I should have none of my products. What else do I know? Well, I'm told it's ammonia, so I'm going straight to that chart of Kb values and looking up a good number for ammonia, which you should remember from the last problem is 1.8 times 10 to the negative fifth. So, okay, now where do we go from here? Let's work on the only number that we were given in this entire problem, and that's the pH. Well, if they're giving me pH, that's found at equilibrium, and usually I could back calculate with my pH to find my concentration of hydronium, but I don't want hydronium, I want hydroxide. So it's a little bit of a more complicated calculation. So here's what I did. I know that pH plus pOH equals 14. So using the pH, I transformed that into pOH and found that that equals 2.63. Now that gives me something a little bit more usable, because from that I can actually calculate my equilibrium concentration of hydroxide ion. So I know that the hydroxide ion concentration equals 10 to the negative pOH. After you plug and chug, that comes out to be about 0.00234. I'm going to layer that into my chart. Now that again is the equilibrium concentration of hydroxide. Now that's very interesting. If I'm going from 0 to 0.00234, that must mean that my change in hydroxide was 0.00234. And it has to be the same across the board, except that since the Kb value is 10 to the negative fifth, there's no change to any initial concentration. So X is going to remain unchanged here, whereas both of our ammonium and hydroxide ion will get to see that change to the concentration since their initial concentrations are 0. So time to fill in the equilibrium concentrations now. So we'll define the concentration of the ammonia at X and ammonium and hydroxide at 0.00234. And now it's really just a simple Kb calculation. So we know that Kb equals 1.8 times 10 to the negative fifth. It also equals product concentration divided by reactant. So that would be 0.00234 squared divided by X. Let's solve for X. I find that it equals about 0.31. So again, without really breaking a sweat, we were very easily able to calculate the initial concentration of the ammonia in this solution.